Good morning, everyone. We'll start per usual with our homework quiz. And keeping with the theme of the last couple days, it's going to be about ice cream as well. So you already know the numbers. The mean ice cream consumption in the USA is 5 gallons per year, with a standard deviation of 1.25 gallons per year. So the question today is, what portion of the population consumes between 3 and 6 gallons per year? Okay, so again, about 3 to 5 minutes to work on that and pass it in. So this would be a good place to pause the video, and then we'll resume when we're ready to go. So for today's lesson, we're going to take a little trip down memory lane back into the probability unit for a moment. And find out an application of normal distribution, something we've already done. So this is called normal approximation to the binomial distribution. And for an example of why we might want to try to do this, we're going to start with this. If you flip a coin 1,000 times, what is the probability that heads would appear exactly 500 times? Okay, we know from experience it should be close to 500 times, but what's the probability that I get it perfect, right on 50%? So thinking back, the way we would do this if we were in the probability unit, say, well, this is a binomial situation because I'm just doing the same thing over and over and over again for a specific number of times. So my number of trials, or n, would be 1,000, okay, and my successes is 500, and of course the probability of getting ahead is a half. So I would write something like this. The probability that x equals 500 is 1,000, choose 500, and then a half to the 500 for success, and another half for the 500 for the failures of getting tails. And I would invite you to try that on your calculator for a moment. But to my understanding, unless you have a much fancier calculator than the one I do, it's not going to work, okay? Specifically because this choose term is too huge. 1,000 choose 500 is way more than a standard scientific calculator can handle. Okay? So how can I figure this out if I really wanted to know what that is? Okay, so we're going to do a little aside here. So to show where we're going with this, we're going to think about what would happen with a small number of trials, where we could actually sit down and calculate it and make it work. Okay. So what I'm going to show you here, this is a spreadsheet I've drawn up. This is for the situation with 5 trials. Okay, so the little bars down here, right, are representing the probability of each situation. So my first bar here, which is like less than 5%, would be getting absolutely no heads. That's 0. Okay, next one is getting exactly 1, which is a little over 15%. The next two are for getting 2 or 3. So that's about 33% each. Okay, and then back down to a little over 15 and down. Now we've only got 6 bars here, but of course it does kind of have a shape that looks sort of like the normal distribution, right? Just very steep and comes back down, but it's higher frequencies in the middle and lower frequencies at the sides. Okay, so let's see what happens as I increase the number of trials. So now I'm going to up it to 10 trials. Okay, you can see it's kind of flattened out a bit, but again, we still got that normal shape. The highest peak is in the middle, so at 5, right, exactly half. And the options around it tail off in both directions. Okay, and as I keep doing this, increasing the number of trials, okay, I get more and more bars, and I don't know, think of this like graphics or something. It gets a little less pixelated, right? It's starting to get smoother, looking more and more like a curve. Okay, if I jump to 50 trials, okay, it's getting even nicer, okay, in terms of smoothness and looking more like a curve. If I jump up to 100 trials, okay, looks even more like a curve. We're starting to smooth out even more. And I have a bigger one over here. And this is the case for 200. Again, starting to look really, really smooth. So the idea is that as you increase the number of trials, this looks more and more like a perfectly smooth curve. So that means that my binomial distribution is getting much, much closer to the normal distribution, sort of that nice curve that we have in the back of the book in the z-score table. Okay, so again, that's summarized here. You don't have to copy this part down. Okay, that's the idea of what's happening. As this increased number of trials gets closer and closer. So to make this approximation work, we're going to need to convert some of the properties of binomial over to what I need for normal. So the two main things are, for normal distribution, right, I need to know my mean and my standard deviation. So the first part here is just explaining how that would work. So for this approximation, we're going to estimate what our mean and standard deviation should be. These estimates are given by my mean is just n times p, okay, which you might recall is the expected value of the binomial distribution. So not surprisingly, my average is just my expected value. Okay, and our variance is NPQ, which means our standard deviation. So this is the important part right here. Okay, our standard deviation is the square root of n times p times q. Okay, so that will give us our mean and standard deviation, so we can use the normal distribution. Okay, the other part, okay, and this is conceptually a bit stranger, the binomial distribution is discrete. So that's the idea of, when I'm looking at these bars, right, I can still see the individual bars as I go up and down. Okay, whereas a normal distribution, like a totally pure normal curve, is a continuous curve. It's completely smooth. Okay, and when we go to the z-score table, right, it doesn't give us an entry for a number. Like, you know, if I look up a z-score of 2, it doesn't tell me what happens for exactly 2. It tells me for how it happens less than 2. So to make the conversion from one to the other, right, to kind of treat the normal distribution as a bar graph, we have to create intervals. So to compensate for this, we consider an interval in the normal distribution. For example, instead of just saying p x equals 5, we're going to go between 4.5 and 5.5. Okay, again, I'm going to show you a little visual to try to explain what's going on. Right, so if this is my normal distribution, okay, so let's say I'm trying to look at 5. Okay, and again, if I try to look this up in the z-score table, it's just going to tell me the value, the percentage for the shaded area below 5, and that's not really what I want. Okay, so to compensate for this, and I apologize, I have to line this up. Okay, to compensate for this, as I say, well, if this was binomial, I would have a bar there. So to make a perfectly spaced bar, I'm going to go half this way and half that way. Okay, just like if I was beside, if I was doing 4 would be between 3.5 and 4.5, and would be like right here somewhere. Okay, so this bar, so the shaded area in that range from 4.5 to 5.5 is going to represent the bar that would represent a value of 5. Okay, so we'll work through a couple examples. Hopefully that will kind of show what's going on. Okay, so for example 1, we're going right back to our original problem. If you flip a coin 1,000 times, what is the probability that heads appears exactly 500 times? Okay, so we'll start with our estimates. Okay, so for my mean, that's going to be n times p. So that's 1,000 times a half, which is 500. Again, which would make sense here, that if I toss the coin 1,000 times, I would expect on average to get about 500 half the time. For my standard deviation, okay, that's the square root of n times p times q. So that's going to be the square root of about 250, which is about 15.8. Okay, now for the conceptual part. Okay, so right here's my rough sketch of the normal distribution. Okay, my target score is 500. Okay, but again, if I try to look this up in the z-score table, it's just going to tell me it's 50 because that's the lower half. So I create a little bar that goes on either side. Okay, and this is going to be between 499.5 and 500.5. Okay, and then the shaded area between those two, which we talked about yesterday, how to get that, that will give us our probability for 500. So that's my next step, is to convert this into a range. Okay, I'm really looking for the probability that x lies between 499.5 and 500.5. So now we can run this through z-scores. Okay, so here are the two side calculations for the z-scores. So for z1, when I'm doing the lower score, I get a z-score of negative 0.03 approximately, and that corresponds to a percentage of 0.4880. Similarly, when I do the other side, it's balanced, so I have positive 0.03, and that corresponds to a percentage of 0.5120. Okay, and as we saw yesterday, the difference between those will be the percentage I'm looking for. Okay, so that works out to about 2.4%. So therefore, the probability of getting exactly 500 heads is about 2.4%. And I guess just for some context, right, so that is the most likely thing that can happen, like as an individual number. But as you can see, right, 97.6% of the time, it's not going to be exactly 500 when you flip the coin 1,000 times. Okay, so that was great because it was all 50-50. So now let's have a look at a situation that wasn't 50-50. So I'm going to go back to my 5 trials on my graph here. And now let's say it was, rolling a dice and trying to get a certain number. So like say rolling a 2. Okay, so now the probability of that happening is 1 divided by 6. Okay, and this is 1 minus b. So 1 minus this one. Okay, I apologize, that's not quite working for me here. Okay, there we go. So it's a little hard to see here because it's so smushed, but basically this graph is no longer normal. Okay, I have my two highest bars right at the start, right? They're both 40.18, and then it goes down from there. So I no longer have a normal distribution. I now have a right skewed distribution. So our approximation does not work for this. Okay, but if I start increasing the number of trials, let's go 10. Okay. That looks a little bit better, although it's still slightly more favored to this side, right? The highest peak in here, so 0 and 1 and 2 are still the best, and it trickles off from there. But if I keep making this bigger and bigger, it does start to look like normal. Okay, it still favors the lower values, but the part that I can see does look fairly normal. And the other ones are so small that they're almost not worth thinking about. So we'll go up to 50. Okay, looking more and more like a normal distribution. Okay, and we'll jump all the way to 100. Okay, so the average is much lower, right? It's our graph before was over here, and now it's here. But I do have that normal shape now. Okay, so when the probabilities are close, that's what happened. Okay, so the normal approximation works really well when p is close to 0.5, right? When it's close to a 50-50 chance of this happening. Okay, and I do want you to copy this part down. Okay, if it's not, so if it's far from half and closer to the extremes, 0 and 1, okay, the distribution is skewed unless the number of trials is really large to compensate for that. Okay, so kind of a good rule of thumb or guideline here is that the approximation will work if both NP and NQ are greater than 5. Okay, so this is something we need to check, okay, to make sure that will actually work. Okay, if that doesn't work, right, if NP or NQ are less than 5, then the distribution is probably too skewed to do this, and you would just have to go back and do the binomial distribution if you could. Okay, so for our final example here, there's a 60% chance a young eagle will survive its first flight from the nest. If there are 30 young eagles at a sanctuary, what is the probability at least 20 of them will survive their first flight? Okay, so we're going to start us off the same way. If we're going to compute this using the normal approximation, we're going to need our mean. So 30 times 0.6 is 18. Okay, and our standard deviation, which is going to be 2.7. Okay, and just as a side check here, right, this was n times p, so n times q, or n times the probability of failure. So nq is 30 times 0.4, okay, and that's 12. Okay, so both np, right, 18 is 18, and nq is 12, they're both greater than 5, so the approximation should work reasonably well here. Okay, so again, to visualize what's going on, I'm going to draw the diagram here. So our mean was 18, and I want to know what's probably at least 20 of them survive. So somewhere over here, right around the first deviation, a little less than that, is where 20 is. And then I want all the values past 20. Now again, if I'm converting this into bars, I would need the bar for 20, the bar for 21, the bar for 22, the bar for 23, all the way up to 30. So that means my starting point, the low first bar, is the 20 bar, so that actually starts at 19.5, and then I just need everything above that. Okay, so in the binomial distribution, I'd want the probability that x is greater than or equal to 20. In terms of our z-scores, that's going to translate into probability x is greater than 19.5. So now we just run through the same thing. We'll check my z-score. So my z-score from 19.5 works out to approximately 0.56. When I go to the table, that gets me 0.7123 out of the table. Okay, now again, that would be a 71% chance that less than 20 are successful. So the probability that 20 or more are successful is about 29% chance. Okay, so that's it for my examples. Okay, there are some examples I'd like you to have a look at in the textbook. Okay, and then the practice work starts on page 311, numbers 2 to 8, 11, 14, and 18. Okay, so thanks for watching. Please make good use of the rest of the period, either to work on this practice or to start work on the assignment that you were handed out yesterday. And I will see you tomorrow.